Oh, hello, old friend. It's good to see you. Let's talk about this word, fascination. It describes an unquenchable urge which compels our hearts to quest and be captivated. As long as there are elegant explanations to complicated phenomena, science will never lose its romance. Over the years, I've traveled the world, indulging in my fascination in physics. And now, I find that a new hunger has woken within me. A fiery need to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicists podcast, and I'm Ben Tippett. And now, allez, physique! I'm going to start this show by presenting you with a mystery. So if you take two mirrors and you push them close together, they'll feel a force pulling them together. It's not gravity, it's something else. And you can do it in an isolated vacuum. So you can put it in a vacuum chamber and suck out all the air so there isn't anything. No wind, no sound waves. Even in a vacuum, these two mirrors will still get sucked together. It's called the Casimir Effect. It's named after the physicist Hendrik Casimir in 1948, who predicted that it would happen. Okay, so what's happening? It's kind of like if you have two ships, so big ocean liners, side by side at sea. So there's going to be waves bumping into the ships from all sides, except for the side that's facing the other ship. So there won't be as many waves between the two ships, and as a result, the waves hitting the opposite sides will end up pushing the two ships together. It's kind of like that in our mirror sandwich, except that there isn't any water, and there isn't any waves. It's just a vacuum. So somehow there's more vacuum, more nothing outside this mirror sandwich than there is inside it. And it's this difference in the vacuum that's pushing the mirrors together. So today, we're going to talk about vacuum energy and the Casimir effect. So the fundamental thing about pushing these mirrors involves kind of the environment that we put them in. Now, who can sort out all the details? Megan Harns works for UC Davis as an environmental education programs coordinator. She teaches kids about the environment. She's a friend of Tia's, and she's been wrangling physicists since she was a freshman. I know of no better person who can help us sort out all the details. Megan, welcome to our show.
Great. Thank you very much for having me, Ben.
All right. So for you today, I've assembled two wonderful titanium physicists. Arise, Dr. Michael Zemcov. Dr. Mike did his undergraduate degree at UBC with me. He did his PhD at Cardiff University in Wales, and he's currently a senior postdoctoral fellow at Caltech working on experimental cosmology. Now arise, Tia Miceli.
Boing, boing, boing.
Tia is a graduate student at the University of California, Davis, where she studies high-energy experimental particle physics, and she's writing her thesis on extra dimensions. All right, so let's start talking about the vacuum.
You know, actually, it was sort of strange because I was at my storage unit a couple of days ago and had a close encounter of the Bernoulli's principle kind. And just sort of struck me as maybe analogous, kind of got my brain thinking in the same way.
Wait, which one is Bernoulli's principle?
Yeah, so the classic experiment that was used to introduce me to Bernoulli's principle was that you have two ping pong balls taped from a thread or string the same distance apart, but you use a straw to blow a stream of air in between the two balls, and you see them actually drawn towards each other because the speed of the air going in between the two balls is faster than the airspeed on the outside of the two balls, and the difference in pressure sort of sucks them together a little bit.
Yeah, actually it's fairly insightful because what's going on is in the Bernoulli principle, you have your two ping pong balls and you're blowing air between them. Let's describe it in terms of a ping pong ball sandwich, okay? So the jam area is the part in between the ping pong balls, and then the bread area is on the part on the outside, okay? Just to help us imagine, okay?
Sounds good.
So there's pressure in both parts. There's a pressure coming from the air, 1 atmosphere of pressure, pushing on this bread side of the ping pong balls. And then in the jammy part of the ping pong balls, there's also some air pressure. Now, because the air is moving when you're blowing through your straw, the air pressure between the ping pong balls is going to be lower than the atmospheric pressure. And so essentially the ping pong balls end up comparing the pressure in the middle of the sandwich to the pressure on the outside, on the bread part of the sandwich. And the fact that there's a difference between the two pressures pushes them towards each other. Your insight's absolutely correct. So what happens in the Casimir effect is there is a vacuum, and the vacuum has an energy, and the energy exerts kind of a pressure. There's a pressure between the mirrors exerted by the vacuum, and there's a pressure on the outside, on the bread side of the mirrors, except that the pressure on the bread side of the mirrors is larger than the pressure in between the mirrors, and this effectively sets up the net force pushing the two mirrors together. It's analogously the same. The only difference is where the pressure's coming from and the reason why there's lower pressure on the sandwichy bit than there is on the bready bit.
Yeah, because in the Casimir mirror example, we're missing an agent that's sort of lowering the pressure in between the mirrors in the same way that the stream of air lowers the air pressure in between the ping pong balls. So I guess my question is, why is the vacuum pressure lower in between the two mirrors in the Casimir mirror example than on the outside?
That's a wonderful question. And to answer that, we need to start talking about what the vacuum is. So when we say vacuum, we usually mean nothing, right?
You sort of get that impression. So you wonder, well, how can energy, exist in a vacuum, or how can a vacuum have a force?
And the answer actually involves a set of arguments that come from quantum mechanics. So to start talking about vacuum, we have to start talking about particles. How particles behave was the historical origin for all quantum mechanics.
We're going to build up to the explanation of what constitutes a vacuum. It's not actually nothing with a capital N, but there's actually exciting stuff going on in there. So to start out, if you imagine a particle in a box and you lower that temperature and you try to get as close to absolute zero as you possibly can, that particle will still have motion, because Heisenberg's uncertainty principle, you can't know its position and its momentum at the same time. So if the particle were to stop moving, you would know that its momentum is zero, and you would know
both, and the world would explode.
So we can't have that. So in actuality, this particle is still moving in the box. So the probability of finding this particle anywhere in the box is represented as the particle's wave function. And this wave function is a mathematical expression of the field of the particle. So all particles are just perturbations of this field. If I look in the box and I see it at one place, I collapsed that probability wave to one little spike, and that's the particle. So particles behave like particles, and they behave like waves.
So we call this the wave-particle duality. So the deal is that in classical physics, back powdered wig days when everybody was holding candelabras and looking at experiments of billiard balls, they would say that, well, you can have energy and motion as a wave, so like waves on a pond or in a tank of water or something, or sound waves. Or you could have these particle things which look like billiard balls and they fly around and they bounce off each other. And what quantum mechanics discovered in the early 20th century is that if you're going to describe the physics of these objects, neither and both mathematical models describe how actual particles or actual waves end up evolving. What quantum mechanics eventually becomes is it becomes a mathematical way to describe the motion of these particles, the evolution of these particles as they move through space, in terms of the evolution of one of these probability cloud distributions. So, the probability cloud distribution thing doesn't really matter all that much for our explanation of the Casimir effect. But one interesting aspect of it is the deal is that we can talk about the energy of the particle either in terms of the particle moving around, but we can also describe its energy in terms of the energy we can extract from the system. So every time it bounces off near the end of one of the boxes, we steal a little bit of energy. According to this picture, there's a point past which you can't steal any more energy from the particle. Okay? Once we extract all the possible kinetic energy from it, it's still moving around in the box. We call that energy the ground state of the particle. Ground because it's on the ground, so it's like a ball, right? If I hold a ball in the air, it'll have some potential energy from gravity. And if it's on the ground, it's got no potential energy left. I've extracted all the possible energy I can once the ball weight is on the ground. So the particle in the box, it'll have a ground state. It'll have a state past which we can't extract any more energy from it. But it will still be moving. It'll still have a little bit of energy to call its own. It's kind of like a bank account, I guess. You know how some banks won't let you extract all the money from a bank account? You need to keep, $100 in the bank account or they get really mad and start fining you.
I know that all too well.
A particle in a box will have some basic amount of money in it, just like the money in the bank account, that you can't extract money past it. It will always have a little bit of energy set aside that you won't be able to withdraw. So,
the place we're trying to go next, Megan, is... So there's this complicated term, which is a quantum field, which is kind of the underlying structure of how these quantum-y things exist and get to propagate around. So one of the things to keep in your mind is that when Ben's talking about zero-point energy and particles and all this other stuff, that kind of lives on a background. And the background it lives on, you can think about as a sheet of balls connected with springs. And basically what happens is that individual particles are little waves in this sheet of these oscillators, which are just these balls connected by springs. So if you think like a table-sized one, I could flick it in the corner and that would propagate across the thing. So different particles are different excitations of that sheet. And then the thing that maps a quantum field to what Ben was just talking about, which is the zero-point energy of something, is that this background, it's never still. Because of the zero-point oscillations, each of these little balls is kind of wiggling around. And so the whole sheet has kind of got this like energy to it that it's just kind of bouncing around, blah, 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 all the time. And that wiggling that the sheet of balls and springs is doing is an energy. You can calculate how much energy would be associated with that system. So that's what that's where we're trying to go with this whole thing, is that there's this background that all these things live on that has an energy to it.
And that sheet is just one of the quantum fields. I mean, there's a quantum field for the electron, for the muon, there's a photonic field, there's one for up quarks.
So my understanding is that the background for quantum particles is sort of in a sheet, and that the sheet is not composed of things that are necessarily woven together, but these balls or particles that are connected in a flexible way to each other, and that their state or their position is going to be relative to how much energy in a wave has been put through that background sheet, but that the background sheet itself is never entirely still because there's always that ground state of energy, and that can be measured, but that it can also be, I think, as Mike said, perturbed or changed with energy inputs into the system, and those spikes are the resulting position or momentum of the particle that you're looking at in particular in that area of the sheet. Am I on the right track?
Perfect.
Okay, let's talk about electromagnetic fields. You know what light is, right? It's a wave in the electromagnetic field.
Oh, I don't know. We've had plenty of discussions and arguments about what is light. But for the sake of argument, yes.
No. Well, what have you taken away from? Can you summarize what you know?
My understanding is pretty simplistic, but while visible light is in a certain spectrum wavelengths of energy between such and such a frequency that we can see. But there's also plenty of other kinds of energy that we can't see without the aid of technology. We could have infrared light, ultraviolet light, microwave light. Light is just sort of a term that we use colloquially to refer to this kind of range of different frequencies that can be picked up by different kind of technologies or the human eye. So when you're talking about the electromagnetic spectrum, you're talking about not just visible light, but the other ranges of light or energy that we just can't see with the human eye.
Correct.
And I got to put in my plug for environmental science here. Plants, of course, very interested in certain wavelengths of light so that they can perform photosynthesis. They need a snack. So I get to talk a little bit about that, but not in as much detail as I think we're going to be getting into in just a minute.
Right. Well, okay. So energy is a really crazy thing in this universe. We were talking about packets of energy here and there and extractable energy. And the deal is that energy can live in a variety of forms. So you could have it in terms of mass, like a weight that has some mass. And you can also have it in terms of a wave. Imagine you have a balloon, you rub it on your head, you charge it with electric charge, right? That electric charge interacts with other electric charges through something we call the electric field. So if I have a positive charge, it will push against another positive charge. And if I have a negative charge nearby, it will be attracted to those positive charges. And then there's a related field called the magnetic field. I'm sure you remember from when you were a kid and you do these fun science experiments. You take a magnet and you put it down under a piece of glass or paper and you scatter iron filings around. They rearrange themselves on the page in loopy magnetic field.
Interestingly enough, I read an article that cows seem to orient themselves along the electromagnetic field lines of the Earth, which can be perturbed if they're next to high-energy power lines.
Oh, really?
So evidently cows are analogous to iron shavings.
That's great. So the deal is that if I take a charged-up balloon, so my balloon is covered in positive charge, and then I wave the balloon around in the air, I end up distorting the electric field. The same way as if I stood in the water and moved my hands around, I'd be distorting the surface of the water. And waves in the electromagnetic field will carry energy away from me waving the around. So anytime I make some motion with my charged balloon, it's going to generate waves in the electromagnetic field, just like ripples of water on the surface of a lake. And these waves in the electromagnetic field are what we colloquially call light. So all light classically it's just this information about a disturbance in the electromagnetic field. Now here's the really crazy part. So you've heard of a photon. Photons are just particles of light. Have you heard that?
Yes.
So the deal with quantum mechanics is we had a very good understanding of what light was in terms of waves. Quantum mechanics said, oh, well, you know what? These waves are actually little particles of light. So instead of imagining a great big sheet flapping around in the wind, you imagine little particles running across the sheet. And somehow the wave-particle duality of the system allows for electromagnetic waves to act both as photons, little particles, and as wavy disturbances.
No, I take issue. The particles are not like little marbles going around on the sheet. What the particle is actually if you were to shake that sheet really hard, fast, like up and down, and you create a very short kind of pulse, that pulse in the sheet would be your particle.
Is your particle independent of the fabric of the sheet or no?
It's made up of it.
It's a coherent disturbance in the sheet. Sorry, that sounded really physicsy. Sorry.
Yeah.
That did sound
right.
really physicsy.
I guess sort of something it reminds me of is my understanding about how waves happen in the ocean, and that, you've got this disturbance in the force, if you will, but that, a wave actually isn't taking one collection of ocean water molecules and crashing it out on the beach until the very, very end. But actually they just sort of oscillate up and down, more or less in place. And it's the energy of the wave that's carried through and sort of bumps these ocean molecules up or down, but that until the wave breaks up on the shore, the particles themselves aren't actually moving all that much. The molecules stay more or less in the same space.
Yeah, so with the ocean wave example, the particle isn't actually the molecules of water. The particle would be the wave, the actual wave that's traveling. And the medium that's traveling in, the water, that's the field. So the particle is actually that disturbance traveling.
So when we're talking about the mirror example, that it exists in a vacuum, as Tia pointed out, a vacuum doesn't mean there's nothing with a capital N inside. So the waves or the energy that's pushing against the outside edges of the mirrors, or the bread of the mirror sandwich, if you will, what sort of particle or background sheet, what's the label? Are we talking about electromagnetic energy? What kind of sheet are we looking at?
Yeah, so that's a good question. So it's all particle fields. Electromagnetic, electron, up quarks, down quarks, muons, tauons. There's a field for each of those. Okay. And so on the outsides of the two mirrors, on the bread side, each one of these fields can have any range of wavelengths. Like you were talking about how electromagnetic light can be in the visible spectrum or the microwave spectrum or the X-ray.
All of them can be present and contributing to the push that your mirrors are feeling on the outside, on the bread side of the sandwich.
Yeah.
So then if these waves are existing and can go through and affect things in a vacuum, what the heck is a vacuum? What's missing?
So it's like this. Imagine yourself with a guitar string, okay? Out in front of you, you've got your guitar. Different wavelengths are possible on the guitar string, right? Depending on how long your string is. So each guitar string is about 1 meter long. So you can get one wave on it, one sound wave, where its wavelength is 2 meters long. And then there's another wave where the wavelength is 1 meter long. And then there's another wavelength where the wavelength is 0.5 meter long. And it goes up and down twice over the course of the guitar string, okay?
And that gives you different musical overtones.
Yeah, so higher and higher notes correspond to shorter and shorter wavelengths. So if this is a quantum mechanical guitar string, something fantastic happens. I mentioned before the wave-particle duality to this. The idea here is that every possible wavelength on the guitar string acts like a particle. You talk about all the different possible waves that are excitable, all the different possible modes that are excitable on the guitar string, and then each mode is going to have its own ground state component, and then if all of the different modes are in their ground state, we call that the vacuum. And that's the definition for the vacuum that we're going to use.
So if I haven't actually plucked any of the guitar strings, but they're just sitting there kind of at their natural energy state, that's a vacuum.
Yeah, that's right. If it's a quantum mechanical guitar string, each of the modes are vibrating. They're just vibrating in their lowest energy state. So the deal is, by plucking the guitar, I increase some particular mode's energy state, and I give that mode a little bit more energy. But at its heart, when I haven't plucked the guitar string in a long time, and so the guitar string's in its lowest possible energy state, if it's a quantum mechanical guitar string, every possible mode is then in its ground state. So every possible mode has a little bit of energy belonging to it, okay?
Sounds good.
So the deal is that, of course, quantum mechanical field isn't a guitar string. It's like a great big cube of Jell-O, okay? You can still make it wiggle. You can still put waves through it. So every possible quantum mechanical field, so electromagnetic waves, electron waves, you can break down the number of different waves moving through your block of Jell-O in terms of individual excited modes. And then if you cool down your cube of Jell-O, each of those possible wavelengths, it will still have a little bit of motion to it. And that motion it's called the vacuum energy, but the state it's in is called the vacuum.
Basically what I got is, if reality is a block of Jell-O, that, if you're adding energy to it and waves are moving through it, you can describe the waves as kind of, the relative strength of maybe the component parts. So whether, it's got a high energy component in the electromagnetic spectrum or a high energy component from, gravity wave, whatever kind of waves are going through, it can all be described. But that if the block of Jell-O gets cooled down enough and doesn't appear to be moving very much, that you would describe all the different kinds of waves that could be going through it as being at their ground state. They're not zero, because as you talked about earlier, if they were all at zero, we would know the position and momentum of the different particles. And again, we can't know that. So if it's cooled down enough, that block of Jell-O will be at its most minimum disturbance, because the waves passing through it will be at the smallest amount of energy they can possibly have.
Wonderful. Okay, so now let's talk about what happens if you have two mirrors that get smushed together. Okay, so mirrors are reflecty, right? Light can't pass through a mirror. It always gets reflected by one, okay? So if you have two mirrors and you put them together, it reduces the number of possible different wavelengths of light you can have between the mirrors. So if your mirrors are a foot apart, you can't have an electromagnetic wave going between the two mirrors that's longer than that 1 foot apart.
It's like Ben's guitar string, where you can't play a note that is deeper than the length of the string.
So the amount of energy that can be passed back and forth between the mirrors is constrained by the distance between them. Similar to the length of the string in the guitar example is a constraint on what the maximum and minimum energy of the wavelength is going to be.
It's an interesting point that you're making here. We're talking about energy. So you can actually pack as much energy between the two mirrors as you want. You just refine to what colors the light can be in. Remember
how you were talking about how there's optical light like green that plants can see, and there's red light, and there's blue light, and if you go to longer and longer or shorter wavelengths, you go into the ultraviolet and the X-ray in one direction, the other direction you go in the infrared and radio, right? So the point is with the mirrors is that there's no maximum, right? Because you can have an arbitrarily high frequency between some finitely spaced things, right? What you can't have is the long wavelength, like we're talking about with the guitar string. So as you bring these things closer together, you start excluding wavelengths that are in the radio, and then you come through the microwave, and then the infrared, and so on and so forth, closer and closer together. So you basically start at the very lowest energies, and as you bring the mirrors closer together, you're excluding higher and higher energies, which means bluer and bluer colors.
In terms of energy, there are now two different things that we can talk about. We can talk about, say, how bright the light is between them, and we can still make the light as bright as we want, but we're stuck. We're confined to waves that have a shorter wavelength than the distance between the mirrors. So this makes a really big difference when we cool down the electromagnetic field between the mirrors down to its vacuum state. So the deal is that between the plates, I'm still not allowed to have red excited light, long wavelength light. But beyond the mirrors, I'm allowed to have as long wavelength as I want. And so the region between the two fields, because it doesn't have all those ground states for the deep, long wavelength light in between the mirrors, there's going to be less vacuum energy between the two mirrors than there will be outside it. And so in essence, that's what's causing the difference in pressure. Even though the system is in a vacuum, even though there aren't any photons wandering around in this system, the fact that I've excluded the possibility of having deep, long wavelength photons between the two mirrors causes the vacuum energy outside the mirrors to be much greater than between the mirrors, and that's what pushes them together.
So, we've been talking about getting the mirrors closer and closer together in a vacuum to exclude the long wavelength sort of energy from being bounced back and forth in between the mirrors. So, at what point can you distance the mirrors or spread them apart enough? Can you have that effect be equalized so that they aren't being drawn closer to each other? Or is the nature of the vacuum such that no matter how far apart the mirrors go, they will still always have less energy in between them than on the outside and will always consequently be pushed together?
Well, I read that it starts to turn on around 10 nanometers, but I'm sure it depends on what the material is made out of and how smooth the surface is.
But that's an experimental thing. But theoretically, anytime you have mirrors that are facing each other, you're going to be excluding some of the modes, and then you'll get this effect. So maybe the thing to think about is Ben's initial example of the two ships on the ocean. And if the ships are really long, then you've got really quiet water in between. If the ships are very short, then you're letting more just of the random stuff in, and the mirrors aren't working mirrors very well anymore. So the problem that Tia's talking about is that basically our ships are very short in the lab. And so you have to get really close together before you can actually start seeing these effects. Because if you pull them apart further, things start getting swamped by just other stuff.
To put it in a different way, we're excluding wavelengths as we get the mirrors closer and closer together, but really long wavelengths don't have much energy to them. So if the mirrors are fairly far apart, the force pushing them together is going to be really, really small, because the wavelengths that you're excluding don't have much energy. So the deal is, the closer the mirrors get to each other, the more wavelengths we'll be excluding, and the larger the difference between the vacuum between the mirrors and the vacuum outside the sandwich will be, to the point where I think you can start really feeling it around 100 nanometers when they're close together. But then if you get the two mirrors really, 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 really close together, what happens is essentially any mirror that we deal with is going to be made of atoms. So if you put these two mirrors close enough together, the little bumps and the fact that it's made up of atoms will start to dominate the overall effect, and the Casimir force will kind of switch off. Well, it'll actually cause them to stick together sometimes. But the moral of the story is there's kind of a range where you can really get a good measurement of the Casimir effect. And when they do experiments, they find that the pressure exerted by the vacuum is exactly the force that you calculated using this picture of different vacuum states outside and between the mirrors.
So there's also an interesting thing, which is that you can imagine other geometries where actually you're kind of enhancing the modes in between, and it actually makes the two things be repulsed from each other. The point is that you're changing the energy density between these two mirrors, and so that is just a pressure, like you were talking about with the Bernoulli effect at the beginning. It's very analogous to that.
The Casimir effect has some ridiculous consequences. So for one, this picture that we've painted is fairly straightforward, right? Any possible wave that I could excite has a ground state, and all of those ground states contribute to the overall energy of the system. Now, in quantum mechanics, we don't care about that. All we really care about is the energy that is accessible from the system. So we care about how much energy I can put in and how much I can take out. And once the system is in its vacuum state, I can't take any more energy out. So even though there's an infinite number of possible waves I could excite, so there's an infinite possible vacuum energy, but here's the thing, gravity. So gravity works in a fairly straightforward way. If something has mass, it causes gravity, right?
Right.
So, question. Shouldn't the universe have an infinite mass? If I can excite an infinite different possible number of waves, why isn't the universe really, really heavy? And they did this calculation, so they said, well, maybe all possible wavelengths aren't possible. Maybe wavelengths can only get so small. But even that the case, they ended up with a ridiculous number. They said that the universe, on average, should weigh something like 10 to the power 60 grams per centimeter cubed. So 10 to the power 60, that's a ridiculous number. That's like, have you heard of a Google?
Yes.
Like one
and
with
besides the search engine. A million millions, if I'm not mistaken.
A million millions, right. Theoretically, using this calculation, there's a number describing how much the universe should weigh. And we've tested it astronomically. We've looked using telescopes and our theory for gravity, and we know how much the universe does weigh, how much this effect should have. The vacuum energy that you calculate ends up being 10 to the power 120 times larger than the number we actually see. So it's like ridiculous. It's more than a Google, more than one with 100 zeros after it, times larger than it should be. Nobody knows why they don't match up. And that's the current problem in physics. It's called the cosmological constant problem, and nobody knows what the answer is. But it's fun. So that's one of the ridiculous consequences. There's another ridiculous consequence, which is that in quantum mechanics, when we talk about energy, it's like I said, all we care about is the ground state. That's like 0 degrees Celsius. I guess 0 degrees Fahrenheit works just as well. It's 0 degrees on a scale. So we're saying, okay, any temperature above that has a positive energy. Now, you've got your two mirrors. The energy density between the mirrors is less than the energy density outside the mirrors because of this vacuum energy. So technically speaking, in these terms, there should be negative energy density. There's a negative mass between the two mirrors. Of course, there's an accounting trick involved, which is that we say that the universe in general has, zero mass, and so as a result, the energy between them has negative mass. But if you can have negative mass, you can build all sorts of crazy things with gravity. You can make warp drives, you can make time machines, you can make wormholes, you can make pretty much anything Star Trek-y or science fiction-y you can imagine. And so there's some question as to whether or not you can make a warp drive using this Casimir effect.
How do you make a warp drive?
That would be pretty awesome.
So we talk about how to make warp drives in episode 9, but the idea behind it is actually fairly straightforward. Positive mass attracts things towards it. So the gravity of the sun pulls everything towards the sun. The gravity of the earth pulls us down towards the earth. But if you have negative energy, negative mass, you can cause a type of repulsion. And so if you play your cards very carefully, what you can do is you can cause the space-time in front of your warp drive bubble to contract faster than the speed of light, and the space-time behind your bubble to expand faster than the speed of light.
It sounds like a jet engine.
It's kind of like a jet engine for space-time. There's a rule in space-time that says that nobody can move faster than the speed of light. But what you can do is you can make yourself a little bubble of space-time where inside the bubble you're not moving faster than the speed of light, but the bubble itself is traveling through the outside space-time faster than the speed of light. And you can do all this using negative energy. And so there's a possibility that you might be able to do it using the Casimir effect.
Fascinating and logical too.
All right, well, that was lots of fun. Thank you, Mike. Thank you, Tia. You pleased me. Your efforts have borne fruit, and that fruit is sweet. Here's some fruit. Tia, you get a pomegranate.
Nom, nom,
Welcome
nom, nom.
to hell. Mike, you get a peach.
Oh, nice. Nom, 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 nom.
Good. Now, I'd like to thank my guest, Megan Harns. Thank you, Megan.
Oh, thank you for having me on. It was a lot of fun.
Oh, great. All right. So, my TIE fighters, let's suppose you want to interact with the Titanium Physicists a little bit more. If you'd like to keep track of us, why not follow us at Twitter at Titanium Physics or join our Facebook group. If you'd like to hang out with us and socialize, why not join our online forum? Go to the website for a link. It's called the Brachio Board. Or if you'd like to send me an email directly to ask a question or propose a topic, email me at barn@titaniumphysics.com. Let's suppose you want to listen to us more conveniently. If you've got an iPod or an iPad, try subscribing to our show in the iTunes Store. And while you're there, write us a review. Your reviews determine our ranking in the iTunes Store, which in turn determines how many new listeners will discover the show. If you have a Zune or BlackBerry, you can subscribe to our show on those doodads as well. So you can download the Stitcher Radio app, which will let you subscribe and listen to your favorite podcasts. Okay, so for all this and more information, visit our website at www.titaniumphysics.com. The Titanium Physicists Podcast is a member of the Brachio Media Network. So if you like listening to scientists talk about science in their own worlds, you might enjoy listening to other shows on the Brachio Media Network, like the weekly Wienersmith, where Kelly and Zach Wienersmith talk to academics about their research, or Science Sort Of, where we all talk about science in the news. Editing support for the Titanium Physicists Podcast is provided by a gentleman named John Heath. Thanks, John. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Until next time, my friends, remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet. Jumped through a window out into the haze.